So our quick look at the calendar. Last class we talked about solving systems of equations using a graphical method. There are a couple of weaknesses of the graphical method. Number one, drawing graphs is kind of time consuming. Number two, the solutions that you get are all approximations, right? We were trying to approximate a point of intersection, and if your graphs are off by a little bit, then the point will be off by a little bit, and you're just making your best guess. So today we'll solve the same kinds of problems, but we'll use algebraic techniques, which are foolproof as long as you do them correctly. We'll get the right answer every time. So we'll start at the top of page 61. We'll go to Kira for the summary. Okay, so we'll start with number one, using substitution to solve this system right here. 6x minus 2y is -3, and 4x plus y equals 5. So the first step here says solve either equation for either variable, and there's a hint, choose carefully to avoid fractions if possible. You can write this if you want to, but this is not how we're going to start this problem. But for example, you could solve this equation here for x, which I don't think is a great idea, and we'll see why in a second. So solving that equation for x, we could first add the 2y to both sides. And then solve for x by dividing both sides by 6. And we have now solved for one variable, which is the first step. But the issue is it's kind of messy because of that division by 6. We're going to have fractions throughout if we do it this way. If we were instead to solve this first equation for y, what would the last step be? Divide by what? Divide by that -2, which is still a fraction. If you solve this equation for x, what's the last step? Is to divide by 4, which is still fractions. But if you solve this equation for y, you don't have to divide, right? And it's because there's this invisible 1 that's in front of the y. And so that's going to be the one that we choose. You don't always get so lucky, but if you are lucky, then you should take advantage of it. So we're going to solve that equation for y, because it will not involve any division. So we subtract the 4x from both sides, and we get y equals 5 minus 4x. Done. And then I'm just going to write the word used next to that equation to remind me that that's the equation that I used. And that's important because in part B it says substitute into the other equation, not the one that we just used, but the other one. So we're going to take this first equation, the one that we haven't used yet. I'm going to copy the entire thing, except I'm going to leave a space where that y is. So we go 6x minus 2 times, and then I'm going to leave a space, equals -3. That's the first equation copied with a big exaggerated space left where the y is supposed to be. And then we're going to take advantage of the fact that we know that y is really the same as 5 minus 4x, yes? So then instead of that y right there, what can we put? 5 minus 4x, because they're exactly equal to each other. So we're going to put 5 minus 4x right there. I'll even put it in red, because that's what it was, that's the color we had it in before. But I'm missing something that I have to bring in at this moment, and it is parentheses. It's because that 5 minus 4x is one thing, even though it's two terms, it's one thing that represents the single y that we had. So it's pretty common to have to bring parentheses in, even though they weren't there before. And then the nice thing about this equation is it has how many variables in it? Just one. And it's a pretty straightforward equation to solve. In fact, I don't really, well, I guess we have to do it because I want to show you how to get the y part of it. So let's go ahead and solve this real quick. So we'll solve that equation. So we'll copy the 6x, distribute that 2. Combine like terms. Add the 10. And then finally divide by 14. So we get our reduced answer of x equals half. Now, if you go back and look at the original equations, what letters were there in the original equations? X and Y. We found X, which is often the end of a problem, but it's not the end of these problems. You need to find two answers. So there are many places you can go to find Y. The easiest place is the one equation up here that says Y equals 5 minus 4x. That's the best place to go, because then we can plug our x equals a half right into there, do some arithmetic, and that will give us the Y. So I'll copy again in red that equation that we had. What was the equation we had? 5 minus 4x, thank you. And then instead of the x, we're putting the half that we just found. Half of 4 is 2, 5 minus 2 is 3. So x equals a half, y equals 3, or a half comma 3. Raise your hand if you've seen this idea of substitution before. It looks like most of us. Great. Any questions on this example? Right. So the procedure is written out there. It's in those steps. So you can just follow those in a little bit. We have one more technique to see today. It's on the next page. Let's go to Lydia for number 2. Thank you. Okay, so let's take a look at number 3. We're going to solve this system of equations using a different technique. We're going to use something called elimination. So in part A, it gives the main idea. It says for elimination to work, and then there's this word that I don't think we've used. Have we used this word this semester? Coefficients? So my fault for putting it here without a definition. These are just the numbers touching the variables. Fancy word for the numbers in front of x or the numbers in front of y. So for example, 3 and 2 are both coefficients, just the numbers in front of the letters. So in order for this new technique to work, we need those numbers in front of the letters. We need the number in front of one of the variables to be opposite of that same guy in front of the other variable. And in order to make that happen, we're going to multiply each equation by something. So for example, suppose that we just decided to focus our attention on the y's. At the moment, the numbers in front of the y's are different, 2 and negative 5. I need them to be the same, but the opposite. Same, but opposite. So give me a number that 2 goes into and 5 goes into is 10. So we're going to turn both of those guys into 10s. And so what can I multiply the top guy by to make it a 10? Is a 5. But you can't just go around multiplying like a little piece of an equation by 5. You have to multiply everything by 5. And so really we're going to multiply this entire equation right here by 5, which is a legal thing to do, right? Multiply the left side by 5, multiply the right side by 5, and that's fine. And then how are we going to turn this 5 into a 10? You multiply it by 2. So we're going to multiply the bottom equation by 2 on both sides, the top equation by 5. So let's try that. So the first equation, that 5 comes in and distributes. So every term gets multiplied by 5. So 5 times the 3x is 15x, plus 5 times the 2y is 10y. That 10y is what we were trying to build. Really common mistake is to forget to multiply the number by itself, by 5 in this case. 5 times 18 is 90. It's really, really easy to just copy that 18, but everybody gets hit with a 5. And then the same idea in the second row. We're going to multiply everything by 2. First term becomes 12x. Second term, minus 10y. That's why we did it. Don't forget, multiply this guy by 2 as well. 18 over there. Okay, so the goal was to make these numbers opposites of each other. So there's a plus 10 and there's a minus 10. So why did we care about making them opposites of each other? Well, if you add these equations to each other right now, we're just going to add straight up and down. 15x plus 12x is 27x, plus 10y minus 10y, 0y. And that's why we did it, is to get those y's to disappear. Don't forget to add on the right-hand side, 108 over there. But again, the idea is that that equation has how many variables? Just the one, and that's what makes it better. Right? We had equations with 2 variables. We traded them in for an equation with 1 variable. Why did it work? Because we manipulated these equations so that when we added these 2 things up, the y's disappeared. If we had just looked at the original equations, it's totally legal to add them up right now. How many x's do you get? 3x plus 6x is 9x. How many y's? Negative 3y's, right? You'll get a perfectly valid equation, but how many variables will it have? Still 2, which isn't any more helpful to us. So it's not that there's a problem with adding them right now, it's just not useful. So we make them have some useful form. Same numbers, but opposite, so that when we add them, they disappear. Okay, the rest of this is pretty straightforward. So solving this equation, we divide both sides by 27. I guess that goes in 4 times, right? Okay, and now we still have to find the value of the other variable. It's the letter y in this case. Unfortunately, finding the other variable using this technique isn't as easy as finding the other variable using the previous page technique. Because on the previous page, remember we had this equation, I think it was 5 minus 4x. And then we just took the x and we plugged it in there, and then it's just arithmetic. But here we don't have any place where it just says y equals. So actually we're going to have to do a tiny bit more algebra to find the value of y. So we know x is 4. You can take that x equals 4 and plug it into any equation that has both x and y in it. So you can go to either the green or red equation. But personally, I'm always going back to an original equation, because if I made a mistake in getting the green or the red, I don't want that mistake to kind of propagate, to carry forward. So take your x equals 4, plug it into either of those first 2 equations. Let's just pick the first one. 3x plus 2y is 18. 3x plus 2y equals 18. That's something we know. So we're going to change that x into what? Into a 4. Plus the 2y equals 18. It's not hard algebra. I'm just pointing out it's not as easy as the arithmetic on the previous page. 12 plus 2y is 18. 2y is 6, so y is 3. Okay, any questions about that elimination method? Raise your hand if you've seen that before. It's like a little bit less than the substitution idea, and that's okay. All right, so last thing before the activity today is about solving systems that are one of our special cases. Most of the time, if you just have 2 lines, they will intersect how many times? Once. You draw almost any 2 lines you want, they're going to intersect exactly once. But we did see 2 special cases last class. If you have 2 parallel lines, then how many times do they intersect? Never, no times. So there were no solutions in that case. And then we had the same line twice. How many times did they intersect? Infinitely many times. And so if you're looking at a picture, it's pretty easy to see if you're in one of these special cases. But here we have no pictures to help us, so we need to know what to look for to identify that we're in one of those special cases. So let's take a look at this first guy. So here, y equals 2x plus 1, y equals 2x plus 3, solving these two equations at the same time. I'm going to do the substitution method because, but let's not do the substitution method. Let's just subtract this equation from the top one, okay? It's the same as adding, right? Adding and subtracting. So when we subtract, what happens with these y's? They cancel. Y minus y is 0 equals, what happens with the x's? They also cancel, and then 1 minus 3 is negative 2. So in this case, we get 0 equals negative 2, which is a surprising thing to see a math teacher write. All right, so we got to figure out what that means. Let's put a pin in that for just a second and come over to this one. Different set of equations. Y equals 2x plus 1, and then 6x minus 3y equals negative 3. If one of the letters is already solved for, I'm almost certainly going to do substitution, because that's the first step in substitution, is to solve for one letter. So let's try substitution on this guy. So I'm going to copy the second equation, except I'm leaving a big space where the y is supposed to be. And then right here, where the y is supposed to be, what are we going to put? 2x plus 1, because that's identically equal to y. So 2x plus 1 goes right here. Okay, so far so good. Now we're going to distribute that minus 3. So we get 6x minus 6x minus 3 equals negative 3. What happens with the x's? Cancel, so we get negative 3 equals negative 3. And then we're stuck, and we don't have anything else we can do, because magically all the variables disappeared. We had x's and y's, and we lost both of them. So here's our big conclusion. It's down in number 6. It says if the x's cancel, I should have said something more general. If the variables cancel, meaning not just the x, but also the y. If all the variables disappear, then that's our clue that we're in one of the two special cases, and they're described right here. If you end up with a false statement, such as 4 equals negative 8, then there is no solution to the system. If you get something ridiculous, like 4 equals negative 8, you are in the parallel lines case where the lines never intersect each other, and so there are no solutions. But if you end up with a true statement, like 7 equals 7, then you're in the case where it's exactly the same line twice, and there's infinitely many solutions. That's what it says there. So let's take a look at these two. The very first example, 0 equals negative 2. What's our conclusion there? No solutions. You can just write that. The first two equations have no solutions. If we saw them on a graph, we would see parallel lines. They never intersect. The second one came up with negative 3 equals negative 3. What does that mean? Infinitely many solutions. If we graphed both of these lines, we would actually end up graphing the same line twice. So that's our answer over here. Okay, so group activity for today starts on the next page. It is quite short. There are 3 problems, which means if you speed through those 3 problems, you can make a major dent and possibly do all of your homework before the end of our class. let's see how far we can get.